So, let's see. Let me get a better marker. Oh, I don't have many markers to choose from. Scheisse. Oh, so chi-square, that's how you say this. That is one symbol, by the way. Never square root that bad boy. It's just, that's the symbol for it. It has to do with that thing I said last, at the end of last class. If you fold over a z-score distribution, you get a sample size 2 chi-square distribution, which is kind of neat. Is everybody with me? So that's 2 is a part of the name. It's a part of the symbol. Okay, I like it. I like it. So let's just do the nuts and bolts. How do I read this chart? And if you missed last class, the real quick summary of this lecture last time was, this is a picture that represents how standard deviations themselves are distributed. That's one use of this. And I really try to get you guys to realize the normal distribution could be means, that could be percentages, that could be sample means. That same picture applies to those different situations. So I started the whole discussion with this distribution, one use of it, and the way to think about it the best about why it looks the way it does is because it's a plot of all the possible samples from a sample of size n. Okay, maybe. So why does it look different than a normal curve? Because the shape of a normal curve is defined by the standard deviation. And if this is a distribution of standard deviations, why the shit would we expect it to look the same? Of course it wouldn't. Okay, I like it. Affectionately called the Jabba the Hutt distribution. Let me see. So let's do a couple examples. And I might as well weave some concept in here too. Let me see if I can do that. I really want you guys to realize there's a lot more you could do with this distribution, but we're just getting into the surface of this. But what we use this distribution for is to compare how well a set of observations fits an expectation. So the problem on the practice final, I think we're going to try that out together in a bit. I'm going to show you how to do all of it in the calculator. But I have an expectation, which I think is kind of unrealistic. But you know the bell curve is always pretty much used to describe grades. You guys with me? You expect not very many people to get A's. You expect a huge portion to be B, C, D. And you expect not many to get F's. So that's that shape. Right? So I could say, here's an observation of grades. How well do they match what the normal distribution would expect? And so I can say, do they seem to match that, or is there evidence that they don't? Okay, I like it, I like it, I like it. Some teachers force them to. I don't understand that. I could just happen to have a bunch of people in my class that already know the stuff, or that don't know enough to really be in that class. I don't know. So it's not always going to look like this. Okay, I like it, I like it, I like it, maybe. So, 0, you would hope that in that case, if we're using this for what's called a goodness of fit, how well do these things fit? How well does our expectation fit with reality? You would hope that 0 would mean they fit perfectly, because this is actually the difference between what we see and what we expect. So 0, if I get a chi-square 0, that means that what we see is exactly what we expected. You guys with me?
Exactly a bell curve?
No. Well, in this case, yes. For this specific case, yes. Right? But in general, it's whatever expectation I had.
Uniform distribution or the other distribution.
Totally. Yes. So the main two types of chi-square goodness of fit we'll see are either we expect it to be uniformly distributed, like M&M colors. We don't expect necessarily to get more blues than reds or whatever. And we're still blue M&Ms, right? Right.
Yes.
And so that's one type, is uniform, and the other type is, like on the practice final, percentages in each category. Or maybe. Okay. So this formula, like I alluded to a second ago, which of you is good? Are you good? No. Ooh. There's that difference I was talking about. So if our observations match exactly with our expectations, we would get a 0 for chi-square. So even if you completely hated the hypothesis tests, I hope to God what you got out of that was this idea of, to show evidence that it isn't something, I have to be really far away from that. That's like the underlying current of all hypothesis tests. So in these problems, there's going to be something that tells me how far away from perfect do I have to be to show evidence that they're not even following each other. That the observations don't follow expectation. Okay, I like it. So when I calculate this, I'm going to compare it to this critical score. So it is exactly like a hypothesis test, but I'm not going to make you do all 5 steps, all that kind of business. Okay, I like it. So, in order to kind of get what I need for this formula, my table's going to look like, let's see, it depends on the day. Observed, expected, observed minus expected squared, observed minus expected squared divided by E. And some of you guys might realize you can just go straight to here, but oh well. Then you want to add those up. So this is another big thing that hopefully we've done enough of. If you cover this symbol up, you see what column you need. I need a column of those so that I can add them up. I love that shit. So let's do this one together, and then I'll make another one for you guys to try on your own. What's this one? This is the last problem on that practice final. Well, that's nice. That fits nice. Oh. So the observed column is pretty simple. Oh, let me move you over. Or I can just put you right here. That looks pretty good. What do I put in the observed column? What do I put right? Yeah. Somebody got that right? I think I checked that earlier, but what do I put right here, guys?
51.
51. Because I actually see 51 A's. Keep going.
63. 131. 60. 36.
So just by looking at that, does it start low, go high, go low again? Yes, so it is roughly normal. So, but is it perfectly normal? One end is not as high as the other end. So this test is, well, how well does it match? And those percentages are rounded. This is a rough, normal distribution test. There are more technical tests to see if something truly is normal enough. Something called kurtosis. Yeah, dude. But we're not going to get into that. That would be a Stats 2 topic. But you still look up kurtosis. If you do an Excel spreadsheet thing, it'll actually tell you the kurtosis of something, and it tells you how far off from being normal some distribution is. So there is something for that. But this is like a surface level analysis. That's why it's so quick to do. Now here, let me show you how to get the expected very quickly in the calculator. So go to Stat, Edit, get into your lists. Let's clear out the first 4 lists. Clear it, Jeff. There you go, buddy. No. All right, let me stop there for a second. If you guys want to play along, you just go clear lists from your drop-down list if you want to do it quicker than me. All right, so let's put in there 51, 63, 1, 37. Okay. Yes. Now, of course, here, how many do I expect? How would I calculate that? How many A's would I expect out of 342 students?
51 divided by 342.
No. That would be the observed frequency of A's. Relative frequency, right?
Oh, Oh, is it?
I want to know how many A's do I expect. If it does follow that distribution, how many would I expect?
342 times point.
Yes. So right here I'm going to put 0.13 times 342. All right, and then I'll just keep going. 0.2 times 342. Are you guys with me? 20% of 342 should be B's. This is what it would be if it followed expectations. You guys with me? Might as well do it all in the calculator since it'll be a lot quicker to do the squaring and the dividing and the adding if I just do it all in the calculator. You don't have to if you don't want to. You can be silly. And then this will be 34% of 342, and then 20% again, and then 13% again. Okay, whoa, what did I do there? 0.13 times 342. There you go. So there's that perfectly low, going high, going exactly back low. That's for a normal curve. Bless you. So what do I make L3 if I'm following this here? We start to fill this in. What would L3 do?
L1 minus
Squared. I like this. So L1 minus L2, you got to put these suckers in parentheses. Now, if you get an error when you do that, it's because you didn't highlight the list. You got to define the whole list. So you got to make sure you have L3 highlighted when you put that in. Let me do it again. Go to L3. Put in there parenthesis L1 minus L2 square. See, this kind of stuff I'm fine with doing the calculator because this is not Math 88. I'm not testing to see if you can subtract and all that kind of shit. All right, so this is perfect. This is exactly what a calculator is for.
Can you do that again?
Sure. Sure. So go up to L3. Make sure L3 is highlighted. At the bottom it says list 3 equals what? List 3 is going to equal parenthesis. List 1 minus list 2, parenthesis, squared. I want to square the observed minus the expected. L1 minus L2. And you guys all with me? Then you can write all that stuff down. Blah, 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 blah. And then you go to L4. What are you going to make L4? Yeah, L3 divided by L2. I like it. L3 divided by L2. Pop. So then what do I have to do to get my chi-square calculated score? Yeah, I just need to sum up L4, because that's the formula. Add up all those. Well, those are in L4. I'm just going to add that up. So I can go second quit and go to list, math, sum like we did before. You do that again. Go to second stat, go to list. I want to do math on my lists. I want to sum up L4. So here's my chi-square calculated. 5.535. It's what I might call chi-square star, but then it's getting kind of crowded up there. All right, this is just like Z star from the hypothesis tests. Now let's go back. Just kind of do this out of order, but I don't really care. How do I figure out how far away I'm supposed to be to show evidence that they're different? What's alpha?
5.
And the degrees of freedom? It's not 341.
4.
Good. They're based on the categories. So there were 5 categories of grades. 5 minus 1 is 4. So let's all see how the hell to use this thing. which I think I said earlier I would do by itself, but too bad. I was lying. So, 0.05. Now, real quick, just to point this out, since this is here, there are these kind of two sides to this, because I could actually do confidence interval. Oh, that looks more like normal. It's okay, Jim. I could do a confidence interval for standard deviation. I could take a sample, get a standard deviation from the sample, and then make a confidence interval for the real standard deviation. So that's why there's kind of like one side of chi-square and the other side of chi-square. That's why there's these here. Zoom out. So this would be one side, and this would be the other side, and then I can make a confidence interval for my standard deviations. That's the other kind of thing that we just didn't have enough time to get into. It would use that very first chi-square formula that I had up here. N minus 1 times S squared divided by sigma squared. Maybe. So what do I get for mine? I know alpha is 0.05. I know that degrees of freedom is, 4? So I have to get this, 9.488, to show evidence that they're different, that it doesn't follow. Remember why that makes sense. 0 is perfectly followed. So if I get above that, if they got further away than that, that's evidence that it doesn't follow expectation. It's so far away from 0, it doesn't follow. Did we get far enough away? I already forgot what it was. 9.488? Yeah. And we only got to 5.535. So we did not make it here. So is there evidence this group does not follow the expected pattern? No. We haven't shown evidence. Does that mean that they do follow the expected pattern? No. We just haven't shown evidence that they don't. Maybe.
For it to follow the pattern, it has to be above 9.488.
No. You can never, ever... Now remember, what can't you ever show evidence of to support H naught? You can never show evidence that H naught looks right. So in this case, I can only show evidence that it doesn't follow the pattern. So in this case, we did not find enough evidence that it doesn't follow the pattern. Sort of like if we say somebody is not guilty, does that mean they're innocent? No. The more you understand that, well, nobody understands that shit. But oh well. Too bad for us. No minority report for us here, sorry. No Tom Cruise, see in the future. Sorry. Alright, so let me make one up. Stop doing my weird references. Let me make some data up and let you guys try it on your own. Made up data. So, actually, yeah, okay, that'll work. Seven categories. 7 levels of something. We have 7 levels. Oh boy. Sorry. Creativity's low. We expect uniform distribution. We observe this. Let's see, 1, 2, 3, 4, 5, 6, 7. So those are the 7 categories. Are you guys with me? You guys all right? Whatever they represent. 7 levels of belt in jiu-jitsu. 7 levels of ability with bowling. 7 whatever. 7 heights of dwarves. Whatever.
Good seasons of Game of Thrones.
Yeah. And then an extra one just to... Well, come on. That last episode was actually Anyway, I like it. We expect a uniform distribution, right? And we observe this. What do you got, Jeff? Just make something up. That's the point. Do it. Can you guys all see those? So that's what we observe. Let me see if you guys can piece together the rest. Right? It's supposed to be uniform. You need to figure out how many are actually up there to figure out what's the expected. Work together. You have enough information to do this. Yes?
We have an alpha value?
Oh, well, if I don't say it's 0.05, let me make it 0.01 just to be different.
But generally speaking, we don't say it's 0.05?
Yeah, you should have picked it up in the book, right? So when it doesn't say it's expected to be 0.05. Most statistical analysis you see in journals do a 0.05. Most. Mostly. Work together. Let me know if you need some